effect on the star it orbits. A star with no planets should drift smoothly through the sky, while one with planets should exhibit a telltale gravitational wobble.
We often say that planets orbit the sun or other stars, but that's not exactly true. The planets and the stars orbit their common center of mass or center of gravity.
And this center of mass isn't halfway between them. Just like on a seesaw, the more massive object must be closer to the center of mass to bring balance to the system.
So consider the Sun and Jupiter. The Sun is about 1,000 times more massive than Jupiter. So the Sun is here, the fulcrum or balancing point is there, and Jupiter is way out here, 1,000 times farther away.
In space, this means that planets trace out large orbits around the center of mass, while stars make much smaller but still detectable orbits.
Here's a hypothetical planet orbiting a star. In fact, they're orbiting their common center of mass. So the planet moves in a relatively large orbit, but the star also moves, but in a much smaller orbit. So the star moves only a little bit, and the planet moves a lot.
I have a somewhat unusual hobby for an astronomer. I'm a belly dancer and fire performer. So it turns out that spinning fire is a great way of simulating the motion of a planet. And the centripetal motion of your fire on the train is very similar to the motion of a planet under gravity. The light on my wrist represents the star, and the spinning ball of fire around that is a planet. And as you can see, the ball of fire draws out a large circle, and my wrist is drawing out a smaller circle inside it.
It's this tiny wobble of starlight that scientists use to find extrasolar planets. But even this wobble would be undetectable if it wasn't for the Doppler effect, the fact that wavelengths get shorter as the object emitting them moves toward you and longer as it moves away from you.
The Doppler effect is very familiar if you've ever heard a train going by blowing its whistle. So, when the train is coming toward you, you hear a high-pitched whistle. And as the train recedes into the distance away from you, you hear the pitch of the whistle get lower and lower in frequency.
Just like sound waves, light waves appear to shift in frequency as the object emitting them comes toward or away from you. Light from an object moving toward you will look slightly bluer. Light from an object moving away from you will look slightly redder.
When the light waves shift their wavelength toward the blue and toward the red and back toward the blue again as the star wobbles around, the shift is excruciatingly tiny. But it's that difference in the wavelength of the light waves coming at you that is what we measure, and it's what allows us to detect planets around other stars.
Using this Doppler technique, Marcy and Butler spent over a decade patiently studying 120 nearby stars for any sign of a wobble.
I went 11 years without finding a single planet, nothing. And no one was surprised by that. It seemed logical to everybody else that it was a fruitless, frivolous, maybe even lunatic exercise to look for planets of any sort.
But then, in 1995, came the surprise announcement
Well, 4 minutes, 28 seconds. Oh, 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 oh. said 4 minutes or whatever, something.
From Swiss astronomers Michel Mayor and Didier Queloz that they had discovered a gas giant planet circling the star 51 Pegasi. Marcy and Butler rushed up to Lick Observatory on Northern California's Mount Hamilton to aim their own telescope at the star and see if they could confirm the Swiss team's results.
Yeah. There it is. It's beautiful. Paul Butler and I were shocked to see that the wobble of the star was precisely as the Swiss had said it was. And I remember driving off Mount Hamilton from Lick Observatory in complete silence, Paul Butler next to me. We knew that the first extrasolar planet had been discovered. It was a very moving, personally moving moment.
This is my first YouTube video ever. Oh, completed a test. Cool. This is where you're found your ball. What? Oh, where was it? The bathroom. Big bathroom.
Doing?
Despite the monumental nature of the discovery, this, like all future extrasolar planets, wouldn't get the name of a Greek or Roman god. It would take the astronomical catalog name of its parent star, 51 Pegasi, and add to it a lowercase b. In this standard nomenclature, if a second planet was found around the same star, it would get a lowercase c, and so on through the alphabet. Its name was the only thing unassuming about 51 Pegasi b. The discovery shook the foundations of our understanding of planets. In 1995, astrophysicist Alan Boss was asked to review a paper announcing the discovery by 2 Swiss astronomers of the first planet orbiting an alien sun.
Good. Stay in there!
Reviewing this paper caused me a fair number of sleepless nights because it was pretty stunning what they had found.
Stunning because the Swiss claimed to have found a Jupiter-like planet. But where Jupiter orbits the sun in 12 years, this planet zipped around its star in only 4 days.
That also meant that the planet would be much closer to its central star, roughly 100 times closer
I don't want it to
than
be
Jupiter.
that loud.
And that just was hard to understand.
Jupiter orbits the sun at a comfortable distance of around 500 million miles. 51 Pegasi b is more like 5 million miles from its star. If it were dropped into our own solar system, this alien planet would orbit much closer to the sun than Mercury, our innermost planet.
Being so close to the star means that the planet is being literally fried. The radiation from the star is incredible compared to what we experience here on Earth, relatively far from our sun. So this was a completely unexpected discovery.
It was a planet that could not have formed there. Astronomers knew it didn't belong there. In the same way that if we found a giant redwood in the middle of Central Park, we would know that it didn't belong there. You'd have to ask yourself, how did it get there? And that's what astronomers were asking themselves about these giant planets that they were finding.
51 Pegasi b wasn't just a freak of nature. It was the first of dozens of so-called roasters or hot Jupiters to be discovered in seemingly impossible close-in orbits. Impossible because the theory for how gas planets form suggests that rock and ice in a disk surrounding a young star coalesces into a solid core that then accretes gas, growing larger and larger until it has cleared out all the planet-forming material in its area. This process can only occur at a distance far enough from the star where it's cold enough for ice to exist.
You can't form something that massive that close into a star. It needs to form past the snow line where ice can form. And in our solar system, that's about where Jupiter is. About 5 times further out.
That's what's on this one too. Go over here. Go over here. 1. I'll put you in the green chair. 2.